Ngalakin Khadijan Nyunga Boja.
Yeah. Talking about US conferences.
I think Zoom still works in China, but many things don't. Star Trek fact.
It's Doctor Who, actually.
Doctor Who.
Got a couple of minutes.
Screen sharing okay? Good.
Yeah, I think it's all working at the moment. As long as the presentation doesn't end, we can keep going. If it ends, it drops out of screen sharing and we've got to restart it. It's all right.
Sort of this presentation starts in window mode, so it probably wouldn't jump out of share.
Oh, you prefer window mode, do you?
No, it's already in window. It's not in full screen mode, it's in window mode.
Oh, right,
So
okay.
It's all good already.
Okay, all right. Okay.
If you're happy, I'm happy.
Yeah, that's fine. All right, I see. Okay. All right, folks, I think we can start. Today, I'd like to welcome Lister Staveley-Smith, who is the Science Director at the International Centre for Radio Astronomy Research, which is a collaborative entity between UWA, Curtin and the state government. Actually, Department of Prime Minister and Cabinet. Office of Science, sorry. So Lister's going to be talking about the Square Kilometre Array and various design aspects related to that. So I won't take up any more time. I'm just going to pass this on to Lister. Thank you, Lister.
Usually clap your lecturers here, do you? Okay.
Yes, lecturer.
Guest lecturers. Well, thank you anyway for the opportunity to talk about the SKA. So I'm a scientist, astrophysicist, but I've been asked to downplay the science side of things.
Recording in progress.
And to upplay the engineering and design aspects, which I will try to do. And please interrupt me with any questions as they come. So some of you might have seen last week, or not, an important announcement. So the Prime Minister was here in WA last week and fairly quietly announced, I think partly because Christian Porter is now the Federal Science Minister and he's not in the good books, I think. But anyway, they announced last week on the 14th of April that Australia is to invest another $387 million on the SKA, the world's largest radio telescope. So why would the government do this and why is the SKA so exciting? I'll try to get some of that across to you today. So the government's view of the SKA is that modern manufacturing is very important for the Australian economy and leads to the employment of tradespeople, engineers and scientists, and is the core of the government's vision to create an advanced economy. And obviously, since the SKA will be based in, partly based in Western Australia, it's going to create quite a few local jobs, and according to the government's forward projections, will attract an estimated $1.8 billion into the economy in the next 30 years. So that's the government's economic rationale, but our rationale is, of course, science. And actually within that very large amount of money, about $64 million comes here to UWA to fund a data analysis centre for the next decade, and the purpose of that is to help scientists process the vast amounts of data coming from the SKA. So that's very important and very exciting for us personally. So this is about my only science slide. I might have another one. So what is the SKA? So the Square Kilometre Array is a radio telescope. It's a telescope. Its purpose is to view distant parts of our own galaxy and distant parts of the universe. The aim of the telescope is to study the history of the universe by looking at studying general relativity in the strong regime, looking at gravitational waves, to look at the cradle of life where planets and stars are born. Are there other civilizations out there? To look at large-scale magnetic fields. Radio telescopes are very good at seeing magnetic fields. To study the universe as stars and the first galaxies were being born, and to look at how these evolved over time, and finally look at cosmology, dark energy, dark matter, all those things that we might have heard about but actually know very little about in detail. Plus, as with anything big, any big major new telescope, just discover new stuff. So in terms of the electromagnetic spectrum, well, we have visible light in the middle there. Radio waves are, of course, very low energy, and the SKA antennas are sensitive to radiation with wavelengths of somewhere between 3 meters and a few millimeters, or a fraction of a centimeter. So it's quite a wide portion of the spectrum, quite a few decades, but a very different part of the electromagnetic spectrum from the optical universe. The SKA is an international project. It involves currently it's hard to keep track of the number of members because some are full members, some are partial members, but approximately 16 members just now, I think. The headquarters, the global headquarters, is in the UK, and we have 2 sites, one here in Western Australia and one in South Africa. So it's two different telescopes on those two sites. And you notice that China and India are big partners, as is Canada, and much of Europe, but not the US. So these are the 2 sites. They're both sites are in semi-arid parts of the world where the weather is benign and the skies are clear. And by clear skies, we're talking about radio wavelengths, of course, so not necessarily talking about clouds. We're talking about transparency, lack of water vapor, not much ionospheric activity, and most of all, lack of things like mobile phone infrastructure, anything which produces radio waves and can interfere with our telescopes. So a bit, getting a little bit down into engineering. So there are actually 2 different types of antenna at the 2 different sites. and the wavelength range of the two different arrays is different, so they're not used together, or at least they're not combined together, which is why it's okay to have them physically separate. So in the South African site, they use what we call dishes. So these are basically parabolic antennas. These are a little bit like your satellite antenna you might have, or your old satellite antenna you might have on your roof. This is an offset paraboloid. And these dishes are fairly big when you compare it with satellite antennas, but fairly small with many other radio telescopes because there's going to be a lot of them. So this is a so-called offset Gregorian design, which means the radiation is focused twice before it gets to the receivers. And it's designed as a wide field of view antenna, so it's actually got a parabolic surface and not a hyperbolic surface or anything fancy like that. So this one is a Chinese design. There's a couple of different designs. This is a sort of Chinese/German design. It looks sort of funnily shaped, but it has got a parabolic surface for reflecting the radiation. So the low frequency component in Australia looks radically different from that, and that's because we're dealing with low frequencies, and it happens to be cheaper to, instead of building a great big parabolic reflector out of steel, it happens to be a lot cheaper to just flatten out the antenna, put individual receptors on the ground, and actually combine the radiation electronically. So these are what we call log periodic antennas, and they have a frequency range from about 50 megahertz up to about 350 megahertz. That's about 6-7 to 1 frequency range, which is quite remarkable. So the sizes of the antennas are commensurate with the wavelength range. These are taller than a person. There's no one standing in the picture here. Excuse me. So they're about 2.5 meters in size. So they're a little bit like a very fancy TV antenna that you also might have on your roof. But they're actually a cross dipole, and that's because unlike natural signals, signals which come from objects in the universe, they've got two orthogonal planes of polarization, so radiation might be oriented, well, it's usually oriented randomly actually. So we need the two linear polarizations to collect all of the radiation from the sky. So different parts of this structure are excited by different frequencies, of course, and all in all it ends up being quite a wide frequency range design. Now, some of this already exists on the site, but most of the SK construction hasn't yet started. These are test arrays.
Sorry,
Yeah.
last question. So that the frequency range is right in the middle of a lot of commercial bands as well, 50 to 350 megahertz.
50 megahertz to 350 megahertz. So you have the FM band at 100 megahertz, but that doesn't exist in the Midwest where this antenna. So we have so by law there is an exclusion zone around this site that's it's frequency dependent, but it's at least 70 kilometers in radius. So no transmitter is allowed to be within 70 kilometers of this this antenna site, otherwise big trouble. So it's a radio quiet zone. We do get something called tropospheric ducting. Under some weather conditions, the radiation from FM stations in Geraldton and Perth can sort of curve around the Earth's surface, but those That doesn't happen very often. What probably troubles us most is, I think you mentioned it, satellite RFI, or satellite signals. We call anything that's not astronomical in origin interference, but of course these are, well-intentioned signals. It's just we don't want to see them. So the main things we have, actually also aircraft, because we're on some flight paths here. Aircraft have some narrowband position. You can actually read the aircraft code and tell where they are, actually. They're very simple codes. There's some satellite bands, communication bands, like the old weather station band at 137 megahertz. I think the big nasty one these days is US military. So US military, I don't know if you know, but they have their own 3G band which operates all over the world. Anywhere you go, you can receive it at about 300 megahertz. Anyone, if you're a US military personnel, your phone in your pocket would pick up a signal anywhere. So that's problematic, and we just have to leave certain frequency ranges alone because it's too strong. But the principal advantage of the SKA is that it's really built on the best sites we have available, apart from the dark side of the moon. So these are the individual elements. What is the distribution of those elements? So in South Africa, we've got these dishes. They're actually constructed, or will be constructed, in this three-arm spiral structure. Why it is, I can go into later in questions if you like, but there's about 200 antennas in this spiral pattern, and that the width of that, or the maximum radius of that spiral, or the most distant element in that spiral, is about 100 kilometers or so. So they're pretty, these are 15-meter dishes spread out by up to 100 kilometers. And it's a fairly similar story with the SKA low. It's the site here is on Buladi Station, about 700 kilometers north of here. And in fact, there's already a couple of what we call SKA pathfinders there, the MWA on the top right, and ASCAP, the Australian SKA pathfinder on the bottom left. So this is part of the radio quiet zone, which we just talked about. And actually since you said you're having network trouble, I won't try to play this, but if this slide is available offline, you can just click on that link up there and do a virtual tour of the radio observatory, get some photographs, and you can move around the site. Also, just seeing the fact we've got a solar hybrid power station just reminds me to mention that being remote, one of the issues is there's no grid power, and all power has to be manufactured from diesel or from this big solar. In fact, we used to have the nation's largest lithium-ion battery here until South Australia bought its one from Tesla a couple of years ago. So that solar energy is stored up in batteries at night, and the telescope is used 24 hours a day, usually. I did have two other slides about science. So using this ASCAP telescope, this SKA precursor telescope, couple of recent discoveries. One is something called fast radio bursts. So about 13, 14 years ago, telescopes suddenly started seeing these intense, brief bursts from objects at very large distances from us. And it turns out that we think these bursts are coming from regions of space only a few hundred meters in size, but are many billions of light years away from us. And it's an inconceivable amount of energy being produced from a tiny, tiny area. We know what its size is because we know what the speed of light constraints are, and we know what the distance is because of the characteristics of the signal. So it's just incredible that we can pick up these bursts from such large distances. And initially they were thought to be some sort of extraterrestrial intelligence broadcasting this, but turns out to be much more likely to be this neutron star emission. Something like a large comet or an asteroid falls onto a very magnetized neutron star and must somehow be able to create this tremendous amount of energy. So these actually help us map out the universe. The other thing we've been doing here at ICRA is to map out more nearby galaxies, and this is a map of about 50 square degrees of sky, and what we have here is an instrument which can map the sky out in 3 dimensions, position on the sky, but also simultaneously redshift. And we've detected hundreds of new galaxies. It might be hard to see on this diagram here, but I can blow it up a little bit in that small region known as a cluster, and we can see how these galaxies, different colors according to different redshifts, interact with neighbors and interact with ionized gas which surrounds these massive clusters of galaxies. So we're really studying what's out there in the universe and how galaxies evolve and how they interact with their surroundings. Right, so just moving on to some design type issues. So there's a couple of different ways one can think of making a big radio telescope. Basically you want to collect lots of radiation because the radiation from the sky is very weak. One approach is to make a giant parabolic reflector. So this is an example of the largest parabolic reflector which now exists. This is the FAST telescope in China, in Guizhou province, in southern China. So this dish was built in a naturally, this is called a karst region. These are limestone hills, and that limestone has kind of caused the hills to sink in these depressions, and some of them are quite conveniently shaped to build a sort of parabola like this without tremendous cost. So this is the Chinese FAST telescope. It's 500 meters across, so it's got a huge collecting area. So it has very high sensitivity. The reflector does the focusing, so there's no not much data rate involved. But against that, being a large reflector, it actually has quite a small field of view. And it also has poor angular resolution. So the resolving power of any optical system is basically the wavelength of the radiation you're detecting divided by the diameter of the dish. And a dish like this, even though it's massively big, doesn't have that much, in fact it's poorer resolving power than the human eye. So the human eye can see more details than a big dish like this can in their respective wavelength regimes, of course.
So just to jump in, so then that's a massive engineering effort, right?
Yep.
So they must have seen some value to it. I mean, that analogy about the human eye is one about resolving power, but so why did they build it if it's not?
So this is pure sensitivity. So this dish is capable of detecting distant galaxies. It's capable of detecting with very good sensitivity these fast radio bursts that I mentioned. It's capable of detecting lots of new pulsars. It's less good at actually measuring where these objects are, and it's hopeless at measuring any structure. Now, some of those objects, like fast radio bursts, we're never going to resolve those, but objects like galaxies. So I showed that map from ASCAP of some galaxies. FAST is completely incapable of actually measuring their structure and what's going on inside. Now you can have, so this is the sort of case study I'm coming to actually. So you can actually, I mean, say you want a given sensitivity in your telescope, you can say that, well, either you want one big dish, or maybe several medium-sized dishes, or maybe lots and lots of small dishes. Now, these are design and cost choices. So I'll just go into those trade-offs a bit more detail in a minute. So the other side of that equation is the interferometer. So you can have an interferometer with the same collecting area as the FAST telescope, and there are some pros and some cons of doing that. But let me just start off saying that this is the ASCAP interferometer in Western Australia, so I use this. This is my main focus of research at the moment. It's only like 1-2% of what the SKA will be, but it's here now and it's more powerful than anything that exists for what it does. So this is producing excellent science. But this is an interferometer, and that means we have to combine the signals from many dishes to make our images. So the pros of interferometers is they have a very large field of view, because each individual antenna can see a bigger portion of the sky. But they have higher angular resolution, and that's because an interferometer, the resolution is defined by the maximum separation of the dishes, not the size of the dishes. Sensitivity comes from the total collecting area. Resolution comes from the sort of maximum baseline. And in this case of ASCAP, compared to FAST at least, it has low sensitivity and it has a high data rate. So low sensitivity is not good for many science applications, but high data rate is expensive. So these are kind of two extremes of a trade-off you have to make when designing something like the SKA. In fact, the next slide just gets into that trade-off. So on the left-hand side, you can either have one great big dish or maybe a smaller number of not so big dishes. And on the right-hand side, you can have a large number of small dishes. And I hope you can see from this sort of cartoon illustration on the right that having a large number of small dishes can be exactly equivalent to having one big dish. You can think of that parabolic surface as consisting of a number of different reflectors, and if you combine these appropriately, in this case a simple summation, the result is exactly the same. But of course you wouldn't actually in practice put your small dishes on a big reflector, and that's a waste of time. You put them on the ground, and it's much, much cheaper to build telescopes, small telescopes on the ground than huge, great reflectors. In fact, the cost of the cost of any engineering structure goes up with greater than the square of its size, more like the cube of its size, so it just makes a lot of sense from the point of view of cost, antenna cost alone, to make your telescope from a larger number of small dishes. And here's some studies that were done a few years ago about, well, what is that optimum? Is it one big dish? Is it millions of small dishes? Or is it something in between? And I think not so surprisingly, the answer is, well, something in between is the right place to go to. So if your science is based on pure sensitivity alone, so you really want to detect something in this part of the universe, it's really, really faint, you need to get to that sensitivity level, you've got so many dollars, how do you, what's the cheapest way of doing it? Well, it's not too bad in this case to build one big dish, but it's actually slightly cheaper to build lots of 15 or lots of 20 meter dishes. And that's because dish size scales with more than the power of 2 of the diameter. So area goes as the square of diameter, but cost goes to diameter to the power of 2 point something. It's close to 3, it's about 2.7 usually. So in this cost equation you can see, so the antenna costs are blue at the bottom of that this histogram. The bottom axis is dish diameter if you can't see it. So antenna costs are very cheap. You know, if you want a 6 meter dish, you can go to well, you could almost go to some store and buy one, but they're very easy to manufacture. Bigger dishes are less easy to manufacture. The other components in the calculation are things like computing, correlator. Correlator is what combines a signal together. Data link, station electronics, short-haul links, antenna electronics. Antenna electronics can be quite expensive because a typical radio telescope, unlike a commercial antenna, typical radio telescope would use cryogenically cooled receivers, and those are pretty expensive. So if you have lots of cryogenically cooled receivers, that's going to be a big part of your budget. So this argues for 15, 20 meter class antennas. However, this is one metric. If you change that metric, and this all comes down to what your science requirements are. So telescopes like the SKA or any instrument or facility has got a number of competing science requirements. This one is a requirement that this requirement is one of survey speed sensitivity. So if you want to survey the sky or a portion of the sky to a certain sensitivity, and you want to do a certain area of sky in a certain time to a certain sensitivity, how much does it cost to do that? The equation changes considerably there because small telescopes have wider fields of view, so that strongly favours the smaller dish diameter. And in fact, that 15 to 20 metres pushes down to more like 10 to 12 metres. And this study, I think, is at least a decade old. 2007 it says there. In the meantime, cost of electronics and correlation has rapidly decreased, data transport, so that optimum dish diameter might be even slightly lower than that. Although this study did take some of that into account. So this very convincingly suggests that, well, this Chinese-style way of doing it is, completely wrong. If this, according to these science requirements, you'd be much better off doing what ASCAP did and we here in Australia did, and to build interferometers with lots of small dishes. But it really does depend on your what the design goal is, what the science goals are rather. Okay, some of the things we have to deal with, whatever the dish size in the SKA is, data rate. So we have huge volumes of data. SKA mid, the dish array, this is about 200 dishes. The aggregate data rate is about 10 terabits a second. From SKA low here in Australia, it's about 2 petabits a second. It's much higher here because, if you recall, the electronics, the radiation is being focused electronically here in Australia, not by these parabolic reflectors. So that data is reduced down in volume after this correlation process to about 5 to 10 terabits a second. And that's the sort of data rate that we can sustain through long-haul fibre links, which already exist between this desert site and Perth. So we have this Pawsey supercomputing centre in Perth, and this data flows, at least from our existing SKA precursor antennas, flows straight into the Pawsey centre. Not at this data rate, this is the SKA data rate, and the SKA data rate is something like, I think we're figures are more like 500 petabytes a year at the moment. So it's a lot of data being produced, very expensive to store that data. The plan is still not to store that data because that's too expensive. Plan is to have this pipeline running in real time which processes the data, makes images of the sky, if you like, cubes of the sky, and then that raw data gets deleted. But maybe in a decade's time it will be possible to keep even that volume of data. Who knows? So, yeah, just a flavour of some of the design development stages for the SKA. So it's not just about antennas, it's about infrastructure in both sites. It's about the science data processor, which is the pipeline that reduces the data and produces images. It's the software to manage the telescopes, control systems in very complex ways. Signal and data transport is probably the biggest cost in this system, is not just the laying fibre in the ground, but actually having data links at each side of that fibre to transmit and receive the data. And the low-frequency aperture arrays and the dishes themselves, as we've seen, the cost of those has been minimised. So that's not necessarily the largest cost of the SKA anymore. Okay, a bit more about ICRA here. So ICRA was founded in 2009 to support the research with the SKA and these SKA precursor telescopes. It's a joint venture of UWA and Curtin and the state government. Headquarters are here. We do research in science, engineering, and data-intensive astronomy. We have an education and outreach team, and we try to encourage local industry to participate in the SKA, particularly now that large contracts are beginning to being thought about. Official construction should be next year, official start of construction. And as I mentioned at the beginning, we're now the host for this recently announced Australian SKA Regional Centre, AusSRC, which itself will be a joint venture also with CSIRO involved. So that will be our sort of largest investment locally for us, will be in this data-intensive astronomy, handling the huge amounts of data and scientifically analysing them. A few, since the focus of your course is on industry applications, just a few quick industry case studies here. So we've done quite a bit of work with Amazon from very early on, using Amazon Web Services. And they provided us early on with a number of grants that helped us to process data in the cloud. And it's still not determined, it's still not clear even now when it comes to delivering things like the SKA Regional Centre, how that will be delivered, where the storage will be, where the processing will happen. And it's quite likely there will be, at least initially, a mixture of hardware here in Perth at the Posey Centre, and also in the cloud. It's whatever does the job in the cheapest way it will do. But bearing in mind the data sets are quite large, so data transport is often quite expensive. So I've mentioned solar already, so we've worked with Balance Utility to look at electricity generation technologies, solar technologies, but technologies with a focus on being radio quiet, so how to generate power without making a noise at radio wavelengths is not is quite difficult. A lot of consumer electronics, switched power supplies radiate a lot of excess emission that's within the band of our telescopes. There's a lot of infrastructure work available at both sites, and it's Geraldton Company we've worked with who've been good at installing cables on the SCAP and MWA antennas, so that's gone very well indeed. And here in Australia we'll be building about 134,000 of these log periodic antennas, which will form SKA low. And final industry case study, I think, is Down Under Geosolutions. So it's a company formed a while ago to process data for industry customers, resource industry customers, but they're now working with us on how to use the computing technology. They use this so-called green solutions involving dunking the servers in oil to cut down on heating costs. So we're working with them on processing algorithms and ways of delivering processed data in short amounts of time. So they're based up the road in Subiaco, but have also got overseas nodes in London, I think, and Houston, Texas. Okay, I might just start winding up now. So just out of interest, what's the timeline of the SKA? So it says their construction starts on the 1st of July 2021. Because of COVID and various other delays, that's extremely unlikely since they haven't issued any contracts that I know of yet. But it will be shortly after that, because the SKA consortium is, and the SKA is an international treaty organisation, and 5 governments have so far ratified it, so that means the money is, the legal basis is there, the money is starting to flow. Australia and 4 other countries have committed. So construction will probably start next year at this rate. But it extends for almost a whole decade, and if you just skip down to the end of construction, July 2029. So that's a fair way to go, although it is going to be built in stages, so we will see early versions of the SKA with much more power to observe the universe than our existing precursor telescope. So I think you'll start seeing science coming out of the SKA much sooner than the end of the decade, hopefully anyway. Just wrapping up. So SKA is an international project, 16 member countries. It's a €2 billion facility, so it's quite a lot of funding is coming into the SKA from countries other than Australia, of course. Australia is our 14% partner. Antenna technologies. So here in Australia we have these log periodic antennas. We have stations which are about 40 metres in diameter, each of which has, I think it's 256 log periodic dipoles. And there's 512 of those stations altogether, and I think that multiplies to give that something like that 134,000 number that I mentioned before. And in South Africa we have these almost 200 dishes. Because we have limited power availability at site, some of the processing that has to be done at site will be done with ASICs, which are application-specific integrated circuits, and some will be done with the somewhat slower but still quite capable FPGA devices. But anything power-hungry like GPUs or supercomputing is probably going to be done where there's cheaper power available. So power is a big thing with the SKA, and in the astronomy community in general, It's not, well, even me as a researcher, I used to fly around the world quite a bit, but our biggest footprint as astronomers in the power that's being used by supercomputers, not by all the travel that we're doing. So that's a big issue which affects, well, virtually all of science, actually. And as we've seen, probably next year for the start of construction, and hopefully we'll see some of it in the middle of this decade and most of the rest of it finished towards the end of the decade. Thank you.
All right, we do have some time for questions. Anybody? I'll start with Norman. Oh, is it? Yes.
Just to clarify, that construction period, you mentioned that will you be able to get results in that construction period, or do you get results after construction?
So I very much hope that we will get results during that construction period, and the reason for being able to do that is because, you know, these telescopes are being built from lots of individual components, so it is the intention to build up the telescope, starting with the central core, then moving outwards. So in that process, it's quite easily possible to, say, get some results with perhaps a low resolution but still very sensitive central part of the array, but wait a bit longer for the full resolution array to come along. So that's of course not possible with a big single dish where you have to finish the thing, but it is possible in this, and it's only possible if you actually do things like schedule the construction during the day, and then at night time you can do the observing, because construction engineers being construction engineers, there's safety issues. They have to have these phones with them, or not phones, but two-way radios, and that doesn't work well in a radio observatory. But if they go home, well, not go home, but if they go to the construction camp at the end of the day, it does leave us some ability to switch on part of the telescope and do some early observations.
So the various phases that you talked about, they are essentially still co-located rather than be geographically distinct?
So the phases here, does this give us any information? So it's effectively, I think you can see there from the middle, like AA2, which is the, what's that, the 1, 2, 3, 4, fifth one down, is building telescopes with baselines mostly less than 20 kilometers. So it's about doing the central components first and then building outwards. So that's sort of the most convenient way that one can get early science results out.
So, given the problems that you've identified, heating, computation, and the government's push for there's opportunities here, what are the opportunities for the next generation of students to solve a problem that would be of interest to ICRA, SKA, so that they could form a company and sell their tech into it? Where's the low-hanging fruit?
So I think technology industries are a good way to go in Perth. There's been a number of success stories with technology startups here, and some of the issues involve, some of the issues that are problematic in all of science research at the moment is the efficiency of code. So we've got computer manufacturers who manufacture components in a certain way, and that's mostly got to do with legacy. But when we or anyone else, for that matter, tries to run their code on these architectures, we actually get about 1% efficiency, and that's just rubbish. I mean, how can you design a computer, any sort of computer, and you're only using 1% of its resources? So it just doesn't make sense whatsoever. So there's a lot of work to be done in that area, and that applies to anything, Microsoft PowerPoint or whatever. But even, the most, we're very careful, or our software engineers are very careful with how stuff is designed. They use GPUs when they can, but we consistently get 1% or a few percent. It's just not good enough. It's costly. It's costing us 100 times more than it should do, and it's using 100 times as much power as it should do. So certainly, algorithmic efficiency is a big one.
So, software companies, firmware companies.
Firmware is a big one too. There's a huge lack of things like, FPGAs are used all over the place here, but a huge lack of people with specialty knowledge in FPGA programming. And I think actually one of our, the Altium company, and it used to be in Tassie, but that guy who started that off was an astronomer, and it's now multi-billion-dollar company. And he sold it off a long time ago, but that's all about designing code to run on FPGAs.
So who's done some FPGA programming? You, as part of a unit here?
Yeah, part one of a unit.
So, useful skills to have, right?
Yeah. Trouble is, it's industry demand for you is very high, and industry salaries are a bit better than salaries at universities.
Yes, but when they start their own company.
But start your own company and you've got it made, yeah.
So the ASIC designs, they're already done for this, or are you looking for people to do ASIC work?
I don't know in detail. I don't know in detail if those design points have been made at that level. So there may be some ASIC versus FPGA decisions to be made now, but for a big facility, ASIC is an obvious choice. You just design something that works with 80% efficiency, it uses much less power, but if you make a mistake in that design or want to upgrade later, then you're completely stuffed.
Your other challenge is that your first tech goes in at 2022,
Yeah.
and your last tech goes in at 2029.
I know.
So 7 years later in the electronics industry is, a long time.
So they've got fairly clever, the SK project mainly consists of system engineers right now, and they're pretty clever about looking ahead, but there's on occasions there's big jumps in technology, a big drop in price that can't be factored in, unfortunately. So yeah.
Pawsey will probably be replaced twice by that point.
Well, the initial Pawsey supercomputer was one petaflop, and now the replacement to come this year is 30 or 50 petaflops or something like that.
Even just companies around the maintenance of this, as soon as you deploy it, it's just going to be a full-time job maintaining it, and then within another 10 years, it'll be an upgrade project. There's the scale of this project is huge, and the opportunity I can see for industries is potentially huge.
Yeah, certainly when we first talked about the SK, it was defining some of the standards that that others aspired to. But these days, when you look at the